All right, so here's the comparison and contrast of strategy and template method. And once I give you the overview, I'll tell you why it's significant. So strategy gives you a nice black box abstraction. And what that means is a good example of a black box use of strategy is the way in which you pass functors into STL algorithms. So you have enough STL algorithm like sort or an STL container like set, and you pass in functors, and you don't know, you don't care how it's implemented under the hood. Now, it turns out you could look at the source code if you really wanted to be completely encyclopedic in your knowledge, but that's not required in order to be able to use those mechanisms. They're black boxes. So that's what strategy is typically used for. It's more of a black box. Template method, you've got to know certain methods need to be overridden in certain ways. So for example, we talked about a couple examples here where you subclass for the verbose mode stuff, and you have to know, oh, I have to inherit from this event handler base class, and I have to fill in the prompt user somehow. I have to fill in the make command thing. You have to know sort of what to do. You have to subclass. So it's more white box. You have to know something about the way in which the framework is actually designed internally in order to use the abstraction. So that's kind of the thing. Another way to look at it, this is more object-oriented programming 101 kind of stuff, but when you're first learning object-oriented design and programming, one of the things you often do, I don't know whether they do this here at Vanderbilt, but one of the things you often do from a modeling point of view is think very carefully about is-a versus has-a relationships. Have you guys been exposed to is-a versus has-a at all? OK, so you know that with, like, let's say we're modeling a car. So you're trying to decide what should the relationship between car and tires be. So is a car a tire? No, not really. Does a car have tires? Yes. So that means probably containment, right? So you think about using containment relationships, and you're going to have an array of tires or whatever. That's the kind of thing you'd have. Conversely, you start trying to do some kind of shapes abstraction for a drawing tool or something. In that case, you have a base class called shape, and then you have circle, square, rhombus, dodecahedron, whatever. Those are examples of is-a relationships. A dodecahedron is a shape. So that implies an inheritance relationship, right? So is-a versus has-a. And that's what you kind of learn when you're first being exposed to object-oriented programming, where you're trying to figure out which features of the programming language should you use. Should you use inheritance here? Should you use composition or aggregation, et cetera? So that's at a programming language level view. When you start moving up to the design level, which is what we're talking about with patterns, you still have the same sorts of issues, except now we think about them more in terms of design properties. So the trade-off between strategy and template method is really very similar to this trade-off between is-a versus has-a. But is-a versus has-a is more localized to choosing language features, whereas template method versus strategy is really about choosing design characteristics or design patterns. So the same sorts of things go into the thinking. So strategy is more about composition. It's more about sort of a has-a-like kind of thing, whereas template method is more about inheritance and extension, so it's more of an is-a kind of thing. And there are pros and cons each way. So you can see here, strategy gives you this nice, clean black box abstraction like we have with STL. You just plug in functors, and you don't have to know much about the details of how it works. If you don't use STL, but you use dynamically bound strategies, then you can plug in strategy objects that can be dispatched at runtime. So that's kind of cool. But for each different separate thing you need to do, you'll have a separate strategy object that does it, but it could be dynamically bound. There's nothing about strategy that makes it inherently statically bound. And it also, the real benefit of strategy is it allows you to mix and match features. So if you have some kind of abstraction, like we saw with the succinct mode versus verbose mode, where there are 4 different things that vary, right? Prompting the user, getting the input, making the command, and executing the command. Those are 4 distinct things that vary. So imagine in general you have 4 distinct things that vary. It may or may not be those 4 things. And each thing that can vary may have k alternatives. So there may be 3 different ways of prompting the user, 5 different ways of being able to get input, 17 different ways of making commands, 3 different ways of executing commands, and so on and so forth. With strategy, you only have to have as many strategy objects as there are different ways of doing things. So it's an n plus m kind of thing, because you have n different strategies or different things that vary, and then you have k different things of each of those variations. So it doesn't get a combinatorial explosion. With template method, as we'll see shortly, you'd have an n times m problem, because you'd have to have a separate subclass for each different combination of features that vary. So that's why you get into some unwieldy designs if you have a complex space. One downside with strategy, there's a little bit of overhead for forwarding, because you're calling things through a strategy object. That overhead is minuscule, by the way, but it's there. And you may end up with lots of strategy classes, which may or may not be a bad thing. You just have to deal with that number of things. And keeping them in sync and making sure they're semantically correct is somebody else's problem. That's the problem of a different pattern, the factory pattern or abstract factor pattern. In contrast, template method, unlike strategy, doesn't require forwarding, because you're just subclassing from the base class and you're just overriding the method. So it's just a dynamic binding call. Whereas with strategy, typically, you would have an extra level of indirection. And there are, again, ways to optimize this, but that's a point to make that distinguishes them. For simple use cases where there's just one thing that varies in a couple of different ways, template method is really simple. It's not complicated to implement. The more things you have that vary, the more complicated you have. You end up with coupling between subclasses and base classes, which is just always an issue with inheritance. You generally want to avoid modern thinking about software design doesn't encourage deep inheritance hierarchies. Those are sometimes called fat interfaces, and you want to keep them pretty clean, pretty shallow, I guess, as opposed to deep. The inheritance hierarchies are static and can't be reconfigured at runtime, so you have to do all this different combination at design time when you write your program. Adding features via inheritance can lead to a combinatorial subclass explosion. As I was talking about before, you'd end up with lots of different variants, each overriding one thing to vary it in subtle ways. So as a general rule of thumb, as a designer, if you have deep inheritance hierarchies, it's probably an indication that either something has gone awry or you have a framework that is doing an awful lot of stuff for you, and you just have to program sort of at the edges of the framework. So strategy is commonly used for black box stuff. Template method is commonly used for white box stuff. You will often find, if you take CS 282 next semester, you'll discover very clearly that oftentimes frameworks do both. So a great example of a framework that does both white box and black box reuse with template method and strategy is the Android Async task framework, which is a cool framework that allows you to be able to run computations in the background without affecting the user interface thread's ability to not block, because in Android and many user interface systems, you can't block in the main thread, or otherwise the event loop starves, which, by the way, is also one of the issues with the reactor. You don't want to have non-preemptive operations that block for long periods of time. So async task allows you to be able to not have things block, and it uses template method to override certain hook methods that run either in the background or the foreground thread, user interface thread, or the background threads, and you can customize what those methods do. So that's template method, because you subclass to get that behavior. But then you can also use strategy to configure the actual type of executor used to run the computations. And you can use a single-threaded model, you can use a thread pool model, you can use a custom thread pool model. There's a bunch of different things you can do, and you can plug those strategies in. So when we talk about that, you'll get a chance to see how template method and strategy get used in the same framework for slightly different purposes. OK, any other questions about that? It's probably more than you ever wanted to know about.
Yeah, does the strategy allow for the same code reuse that available that template does?
Sure. In fact, arguably it leads to more fine-grained code reuse. Think just a simple example. In STL, you've got the functors. You have a whole pile of functors, right? So plus, minus, divides, lots of them. Or less, there's less, greater, all that stuff. And all those things are just reusable strategies, and you can mix and match them in all kinds of different crazy ways when you do things like passing them into algorithms to control whether they sort in ascending or descending order, pass them into containers to control whether it's stored in ascending or descending order. Those are all totally reusable little widget things that have computation associated with their method call operator. OK, any other questions about template method versus strategy, or anything else we covered there? All right. Let's see. People asked a good question in office hours too. What is preemptive? So preemption, anybody know what preemption is? What is preemption? That's premonition.
Preemptive is kind of in anticipation of something else. So if you launch a preemptive strike, you're assuming that they're going to strike you, so your response is to strike them first.
That's a great definition of preemptive. It doesn't have to do with what we're talking about, but it's a great definition. Let me narrow my question. What is an example of preemption in the context of computer science and concurrent systems? Yeah.
Well, if a program gains a lock on something, then they preempt any other threads from being able to do anything.
That's getting closer. So non-preemptive means runs to completion, not distracted or disturbed by anything else, continues on its way unfettered by any other concerns or demands on its time. And you probably have that in your everyday life, right? You get into a mode where you're studying for an exam, or you're working on a program for CS 251 or something, and all the other things that would normally occupy your time, like responding to Facebook or tweeting with people or whatever you're doing that disrupts you and keeps you from focusing on your anointed task, all of a sudden you go into non-preemptive mode, right? You're in the zone. So that means nothing is going to interrupt or distract you from accomplishing your task. You keep going till you're done, right? Preemption is a concept that shows up in operating systems, especially operating system schedulers, that allow each thread that's capable of running a short snippet of time, maybe 50 milliseconds or 10 milliseconds or whatever, to do its thing before the operating system scheduler preempts it. So if you have multiple threads running in your smartphone or in your operating system or your laptop or whatnot, each of the threads that's running gets a short period of time to do its thing, and then the operating system preempts it, and it puts that guy to sleep and then picks someone else to run. So that's what preemption is. When you take CS 281, you'll learn about it. If you take CS 282, you'll learn about that as well. So non-preemptive means not going to be interrupted. So the reactor, when it's a single-threaded reactor and it's doing callbacks to handlers, to event handlers, uses a non-preemptive model, which means that as long as that callback is doing something, the reactor won't do anything else, which could be a problem if the time taken to do something is longer than the arrival of the next thing to do. Because if the next thing to do arrives before you're done and you're not preemptible, the others just have to wait there. No matter how important their needs are, they're going to wait. So that's the issue of non-preemptibility. Any questions about that? You'll learn more about that in the CS 281 and 282 classes. OK, let's see if there's anything else. I'm trying to remember if there's anything else I wanted to cover related to the programming assignment. So the final exam will basically be like 4 quizzes. It's four or 5 quizzes worth of stuff. The best way to study for the final exam is to look at the quizzes, which reminds me, we should probably also go over the quiz. And anybody, for once, people who are on the ball have a little bit of extra work. People who are procrastinators don't. I'm not sure whether this is a good pattern to incent. But the person who graded the quiz was overly harsh in a few places and took off more points than he should have. So he is regrading some of the questions about examples and known uses to be more consistent with what we actually talked about in class. So if you have not picked up your quiz, you shouldn't notice this as long as you wait till after class to pick it up, which you probably should. Anyway, if you did pick up your quiz, please take it back to Pankaj, and he will regrade it and give you the points back for things that were answers we talked about in class that he took points off for. Mostly having to do with known uses of the command pattern and maybe the abstract factory pattern. Questions? OK. So let's go ahead and talk about the next pattern. This hopefully won't take too long. We should be wrapping up soon. Yeah, we'll do that when I get done with this. I want to make sure we cover this. So what we're going to talk about today is the state pattern. And it's a really cool pattern, very specialized in its applicability, but it does come in handy in some cases. The state pattern is basically going to be used in order to ensure that the commands we type in at the command line obey the appropriate protocol for command ordering. So we want to make sure that the commands we have are executed in the right order. And so we're going to use the state pattern in order to do this. And what we're basically going to do is we're going to bake in the appropriate ordering into the class design itself. So we're not going to have some complicated state machine. We're going to have a very simple state machine. And we're going to push the complexity into the structure of the classes themselves. And so as we'll see here, we use the design of the classes to explicitly order the correct application of user commands. First of all, let's make sure we know what we're actually talking about here. So what we want to be able to do is make sure that we don't try to run the commands in the wrong order. And you can imagine, I'm giving this as an example in the context of our expression tree application, but the general point is more obvious. There's lots of things where you have to do things in the right order. So in our particular case, after you go ahead and type in the format that you want, like in order format, you have to give the expression before you try to print the expression. I mean, that's kind of obvious, right? You can't try to print something you never gave. So if you try to print, if you type the print command before you type the expression command or the expr command, the program will come back and say, hey, you're doing things in the wrong order. You're in the wrong state. That's what's called a protocol violation. You did things in the wrong order. So what we want to be able to do here is keep track of this stuff. And the way it's going to work is we're going to use the state pattern to keep track of which operations are legal depending on what state the object is in. So we're going to have basically a thing that keeps track of the state of the program. And it's going to be called the tree context or the context. And that's going to be used. And when you make operation calls, depending on what state you're in, the operations will actually do different things. It's kind of cool. So here are some of the constraints for our particular program. Format must be called first. Expr must be called before print or eval. Print and eval can be called in any order, and so on. So the way you do this, the way you ensure that this works properly, is you represent the history of the commands as a state machine. Now, hopefully, did you guys learn about state machines yet in 201 maybe?
Digital logic.
Digital logic. OK, great. So state machines are obviously extremely important at the hardware level. They also are often useful at the software level. And sometimes they're a very effective way of keeping track of complex paths through code where you have lots of different states to keep track of. Anytime you start implementing networking protocol stacks, for example, state machines are very important. If you're building threading implementations, things like POSIX threads or Java threads, states are very important, and so on. So in our particular case, we're going to have a couple different states. We're going to start out in the uninitialized state. And when somebody calls format, we're going to transition into the ordered uninitialized state. So what this means is that I have a star there because it could be in order uninitialized state, pre-order uninitialized state. It all depends on what the format was, right? In order, pre-order, and so on. So you tell what the format is, that transitions you here. Then when somebody actually gives an expression, the make tree method gets called. And then we transition into the order initialized state, because now we've actually got the actual contents. We have the actual expression at this point. And then there's a bunch of things that can be done if we are in that state. We can do print, eval, we can give another expression, we can go back and do format again, and so on and so forth. But what this is basically doing is it's encoding the legal operations at any given point. And so the edges out of a state or a node here, the edges that come out tell what operations can be invoked legally at that point. And if you invoke the wrong operation, then you get an error message of some kind or an exception. So what we're going to do in order to represent this is we're going to take this state machine here, these are the states that we've got, and we're going to cook them into the design of our class hierarchy. So we're going to have this thing called the context. This is all, of course, straight out of the pattern from the book, the Gang 4 book. We have something called a context. And it's got a bunch of operations defined on it. And then we have this thing called state. And this is a base class. As always, things always look the same in Gang of 4 patterns, right? They all have the same sort of shape. So methods are called here. And then those methods delegate to the appropriate corresponding method in the state hierarchy. And depending on what state you're in, these methods will do different things. So if you're in the uninitialized state, then you can really only go ahead and format. If you're in one of the order uninitialized states, then you can really only do make tree. If you're in one of these states, you can do pretty much everything. So depending on what level in this tree of states you're in, you're restricted in what you can actually accomplish, even though the interface looks exactly the same. And that's kind of cool. So here's what it looks like. Here's the context class. Now, just to be confusing, I don't know why the Gang of Four did this, but the word context means different things in different, exactly. So in the context of the strategy pattern, the context was kind of a blackboard, global blackboard, where you wrote stuff that you needed for the strategies to do their thing if it didn't fit with a one-size-fits-all interface. In the context of the state pattern, context is really the same interface that the states have, except it is used to provide the vehicle for delegation. And we'll take a look at that in a second. So here's what the interface looks like. It's got all the operations that you would expect as commands. So format, make tree, print, evaluate, and so on and so forth. The commands that are made actually end up holding a context and forwarding to the appropriate method to get the job done. And then so we have the user command methods, and then we've also got setters and getters for the states. We'll see how those guys get used in a second. Here's what the state class interface looks like. So again, going back to what I was showing you before, we have context, we have a state hierarchy. So this is sort of the interface, if you will. This is actually very similar to the bridges interface in a sense. So state's kind of funky because it kind of combines some properties of bridge with some properties of strategy, but it actually also has this concept of history that neither of the other patterns have. Here's the state class interface. Notice this has the same method names that we have for the context, format, make tree, print, evaluate, and so on, with one difference. These methods are delegated to from the context, and so the context passes itself in to every one of these methods. So you can see where it says et context, context, et context, context. The context is actually passing itself in to all the state methods. And it's doing this so the state methods, before they're done, can update the state that the context uses in order to figure out who to delegate to. All right. So this particular crazy way of organizing things is called the state pattern. And what you basically have here is you've got the context, which is actually kind of like the bridge abstraction class. And then you've got a pointer to, or a ref-counted pointer, like a ref-counted handle, to the state hierarchy. So this is kind of like the implementer hierarchy in bridge, or it's kind of like the strategy hierarchy in strategy. And then you have different implementations. And this guy's going to call it, state arrow handle, but it's also going to pass itself in to the handle. So the handle method that does the work gets access to the context that called it. And that's where the state magic takes place. So in our context, for the expression, we have a context class, a state class, and then we have different kinds of states: uninitialized state, pre-order initialized state, et cetera, et cetera. So here's a little bit of snippet of this code. If you take a look up here, you've got the make tree method. That's the context interface. And so if somebody types expr, expr, that turns into the expr command, expression command. And that expression command basically turns around and calls context's make tree method. And of course, under the hood, that actually triggers the interpreter to take off and parse the input, build up the expression tree, blah, blah, blah. But all we care about right now is that we're going to be doing this work. So make tree gets called, and what you can see it does, it goes ahead and forwards to state make tree. Now, if you're in the uninitialized state, in other words, you haven't typed the format command yet, if you try to call the make tree method in the uninitialized state, an exception is going to be thrown, because that's just an invalid operation. However, if you type format, then you transition to a different state. And now if you call make tree, the right thing happens. The interpreter gets called in order to interpret the input. So the point here is that the context object is keeping track of the history of the operations that have been run, and it's adjusting the state pointer to point to the right subclass depending on what state you're in. So here's the in order uninitialized state. Notice that when the make tree method gets called here, this is an error. But once we've typed the format command and we're in the in order uninitialized state, because we said I want the in order format, notice then what happens is when make tree method gets called, it goes ahead and does the interpretation. So if you take a look at your code, by the way, say it doesn't do the state pattern, but the interpreter gets called in a similar way. for the grad version. And so what this does is goes ahead and interprets the input, and once it's done, it then goes ahead and it updates the state of the context to be the next state to transition to. So you start out being uninitialized because nobody typed any commands. If you type format command, you're now in this case, the in order uninitialized state because you haven't said what the expression is. You haven't initialized it yet, but you know you're doing in order processing. When someone types expr after typing format, this method gets called back. It goes ahead and interprets the input, and then it turns around and says, OK, I am successful. I will now create a new state, and I'll make that the new state. And notice the delegation that's taking place here. It's calling the state accessor method, the setter method, in the context that was passed in as a parameter from the context method to update the new state. And that means next time someone types a command in, it'll end up triggering the right operations because you have transitioned states at that point. Yeah?
This seems like a lot of classes in the hierarchy. Why did they not go with just use a singleton to keep track of what state you're in?
Oh, great question. Well, so I think there are two issues. One question is, why would you use singleton or not? And I mean, the one question is, would you use a singleton or would you not use a singleton? And the other question is, how do you manage the states? Because those are really distinct things. So you would use a singleton, independent of whether you have lots of classes or few classes to manage the states. You would use a singleton if there was one and only one thing in your program that managed states. So in this particular case, we conceivably could have more than one thing that managed states. You might have two different things that are managing states independently of each other, and they both need their own state, to use the word that's getting overloaded at this point. They both need their own information. So a singleton would only allow you to have one of those things. So singleton won't help you with what I think your real question is why are there so many classes? And the reason there's so many classes is because you have to have different classes for the different states. So just stepping back for a second here. So the reason we have so many different classes is we have these different states in the program, and each state has a branching factor that will do different things depending on what state you're in. So when you start out in the uninitialized state, all the methods are still here. Format, make tree, print, evaluate, quit, etc. Those are all still there, except only format does anything sensible in this state. So this method here, format, is actually going to do something. And what it's going to do, it's going to transition you into one of these states. But if you call, I don't know, expr when you're in the uninitialized state, an exception is thrown. So even though the operation is still accessible, you're not allowed to use it. Here are some other examples, maybe not quite so convoluted examples that might make more sense. If you deal with file I/O, anybody here ever open a file and read and write to a file? Hopefully you've done that. That's a pretty common thing to do. So what's the protocol for using files? What do you have to do before you read and write to the file? You have to open it, right? But the methods that you have, let's say for sake of argument we have an object-oriented file abstraction. You might have an object-oriented file abstraction. We have a class called file, and you've got open, close, read, write. So the interface gives you 4 methods. But it has in the documentation, it says, don't call read and write until you call open. But what happens if you call read or write before you call open? Well, something goes wrong, right? And that's because it's in the wrong state. So you can imagine a state implementation of a file class that would have a file context, which is the interface, and then it would have a state hierarchy that would keep track of what state you were in. And these states are very simple. It's either file is open, file is not open, right? And so if the file is open, then calling read and write operations do something sensible. If the file is not open, i.e. the state is not open, then read and write operations need to throw exceptions. But the interface is still exactly the same, right? You still have open, close, read, write. It's just that the behavior of those methods varies based on the state, based on the order in which they're called. That's maybe a little bit simpler way to grasp what's going on, but this is still the same idea. And so your original question, Lawrence, was why are there so many classes? It's because we need to represent the state transitions in the form of classes.
Why do we do the inheritance in this way, where level order initialized state inherits from uninitialized state way up the tree?
Yeah, great question. Because we end up being able to reuse lots and lots of stuff. in particular, there are a bunch of methods here that are no-ops, that like throw exceptions. And so we only have to override and fill in the ones that actually change in some sensible way. And all the other ones that are still invalid, they still get the inherited, throw an exception because something bad happened behavior. So we're reusing error handling, I guess is the best way to put it. But you guys are, you're asking some really good questions, and we can talk about this in terms of consequences. So the good things about this pattern is you have different state-specific behavior for different states. So it's easy to tell once you've wrapped your head around the pattern and you've broken your design up in terms of states. You can say, here's the behavior of the system in this state, and there's the class that implements it, right? So there's a very easy mapping from the design space of state transitions into the design of your code. It also makes the state transitions explicit. They're actually baked into the design. You can share the state objects. That's a little bit of an implementation detail. You can use reference counting and things like that. The hard part, which I think is really the question, is how do you keep track of all these classes? There turn out to be a lot of classes for the different states. And especially for complex state machines, it's not hard if you've got, file is open, file is not open. 2 basic states, 2 subclasses, not a whole lot of complexity. If you start trying to use this pattern for something like the TCP/IP state machine, where there's lots of operations and 30 states or something like that, it gets out of control. And it's even more complicated if the states change a lot, if there's perturbation in states. And now, having said that, try writing a non-pattern-based solution to that problem. It's also really hard, too. Go look at a TCP/IP implementation sometime. It's really complicated. And it's lots and lots of special cases and weird hacks and stuff like that. So when you start wading into certain complexity, it all depends on where do you want to draw the line as far as how do you address the complexity. One way is to address it with the structure of the program. That's often where these kinds of patterns play off. Other times you want to make the algorithms more complicated. In the case of state machines, there's often tools that automate this stuff. You can think of Lex and Yak, in fact, or Bison or Flex or Antler or whatever your favorite tool is, as things that kind of bake in state machine models with a higher level domain-specific interface. How do you figure out who does the state transitions? Is this done by the state implementations themselves? Is it done by some kind of table lookup? Table lookup is generally takes a bit more work to set up, but it's cleaner to work on. How do the state objects destroy themselves? How is that managed? Reference counting is probably not a bad idea. There's a great paper called Delegation in C++, written in the Journal of Object-Oriented Programming many, many years ago. I was actually doing my PhD when this article was published, and I was doing my PhD on protocol processing, and I really liked what they talked about. I think, I'm not sure if you can find it easily online, but it's a pretty cool paper. So if you have a chance to get a hold of it, I strongly recommend you do so, because it'll help explain some industrial strength uses. OK, and then the last piece of the puzzle here is just recapping this. So what does state pattern do? It ensures in our case, it ensures commands are executed in the right order. And it does that by building those things into the design of the software. OK, any questions? I did want to cover one set of things real quick here, because we didn't quite have a chance to do it yesterday, or last time, on Monday. So we had a little summary section at the end, and I just wanted to kind of recap all this stuff. OK, so sometimes things are more meaningful if you've had to suffer with the alternatives, right? Someone once said, Winston Churchill once said, democracy is a lousy form of government except when you compare it to the alternatives, right? So some of the people who are most vociferously anti-communist are people who grew up in the former Soviet Union or in China and who were repressed. You really find out, or the Eastern Bloc. Boy, you meet a bunch of rabid anti-communists, talk to people who had to suffer with that, right? So democracy, capitalism has its downfalls and quirks, but wait till you see the alternatives, right? In this case, we're talking about algorithmic decomposition, not political structure. And so basically, the improvement here is over algorithmic decomposition, which tends to program yourself into a corner. Unlike the designs that we saw before that were based on algorithms and algorithmic decomposition and top-down refinement, Our approaches are more modular. Things tend to be hidden behind abstract interfaces. The domain is much more closely aligned to the design and vice versa. And there's also less space overhead because we don't have to worry about keeping pointers for things we don't actually use. There's other places to go to find out more information about this stuff. The design that we came up with, and if you take a look at your code when you finish assignment 4B, it exhibits high pattern density. Almost everything in there has a reason to be there, and it has a reason to be there because of some pattern that helped to dictate which part got connected and how. So you can see things like prototype, iterator, visitor, bridge, adapter. All these patterns tend to get used together. They also help to take complex designs and break them down at a higher level of abstraction, so you're not looking and thinking in terms of individual classes or methods in isolation. You're thinking about groups of patterns that are connected together. By the way, this will definitely pay off. It may or may not make a lot of sense at this point, but when you go to later upper division courses and you're building bigger systems, the pattern-oriented thinking really helps to scale. You'll come back in a year or so and go, wow, that really helped. Didn't make any sense at the time. That's one reason why we keep all the videos online, so you can go back and watch this stuff if you need to get a refresher. We can realize these patterns in languages, bake them into the code, range-based for loops in C++, for each loops in Java. They're very similar. In fact, if you were to look at the Java version of the expression tree program, it's essentially pattern compatible pretty much 100% with the C++ version. The implementation, of course, is slightly different, but the design is almost identical, which is pretty cool. There's also lots of other good examples of patterns in C++ and Java at this website. So I recommend if you're really curious about seeing more Gang of 4 patterns, take a look there. OK, and that is that for the slides. I've never actually sort of finished up the last set of slides right at the end of the class, so it's kind of exciting.